Okay, so in today's video we're going to be looking at logarithms, and usually at the start of this lesson in class I play the video, which is what the QR code link is here. So that QR code is printed in your notes, and you could use the camera on your phone to access the video. It is a video, if you want to search it, by a woman called Vi Hart, and it is called I Love Logarithms. Oh no, it's called How I Feel About Logarithms, I think, something like that. Anyway, I'll link to this video in the description box. So if you haven't watched that first, I want you to pause this video or stop this video and go and watch that first. She talks quite quickly, and usually in class I say, I don't want you to worry about, if you miss one or two things that she says. I want you to watch what she says, and see what you can follow and see what you can take from it. Okay, that's really what's important. So please go and do that and then come back here, because I think she gives a nice number sense of what a logarithm is about, and her videos are really nicely presented too. You'll see what I mean. So go and watch that first, and then come back here and we can have a chat about logs. So hopefully now you've been to watch the Vi Hart video. So it's really about thinking about a different way of counting, or not a different way of counting, but thinking about when we're working with powers and how we're counting by multiplying rather than counting by adding. Okay, so it's sort of a different way of counting. She talked about a system that counts in a times 2 kind of way. How many steps would it take to get to 3? And that's essentially what a logarithm is. So as at the end of the video, she went back and crossed out all her system that counts abbreviations and changed them to logs, and that's exactly what logs are. So if we're counting in, so for example, I'll come back to the information above, but if we think about this, log base 2 of 8 is equal to 3, and that is because if we're counting in steps of times 2, how many steps does it take to get to 8? It takes us 3 steps. Okay, 2 times 2 times 2 to get to 8. So in terms of notation, we have this would be read as log to the base a of x, or log base a of x. Okay, I want to be really clear about this, because this is an error that I see students make a lot, and it's something that they've actually commented on in a VCAR examiner's report a couple of years ago in terms of incorrect notation and not being okay. When you write this, if you imagine, let's go back to primary school, let's imagine we've got our, special lined paper for learning to write. Okay, so we write our lowercase letters down here and our, and our capital letters up here. Okay, so thinking about that, the word log, abbreviation of logarithm. Okay, so you're going to have your word log. The base A is a subscript, so that is written in a smaller font below the word log, but then the thing that's in the log is the same size text as the word log. Okay, so log base A of x, okay, log base 2 of 8, for example. So the, or even you could write the 8 as tall as the L if you want. But the point is what a lot of students do incorrectly is they write log base 2 and then they write the 8 or as a power. Okay, so the 8 should be on the same plane in the same size text as the word log. Okay, it's really important. It's not, you're saying something different by writing it as a superscript. You're suggesting it's a power and it's not a power. So I really want you to make sure that you're careful about that as you work through this, and that you get in the routine, you create the right habits from the outset here. Okay. So let's think about some of these logs. So as we said, log base 2 of 8 is equal to 3 is how we would read that first statement. In a system that counts in a times 2 kind of way, how many steps is there to get to 8? There is 3 steps. The other way you want to think about it is essentially thinking about exponentiation or exponents. If we've got 2 to the power of what is equal to 8 is the same way of asking that question. If I'm counting in a times 2 sort of way, how many steps to get to 8 is the same as saying 2 to the power of what will give me 8. Okay, log base 2 of 32 is equal to 5, and that's because 2 to the power of what is 32, 2 to the power of 5 is 32, and so log base 2 of 32 is 5. So each of these have an equivalent exponential statement. Okay, log base 2 of 8 is equal to 3 because 2 cubed is equal to 8. Okay, It's the same information written in a different way. In the same way that 2 plus 3 equals 5 is the same information as 2 equals 5 minus 3. It's just written in a different way. Okay? In the same way that 3 times 4 equals 12 is the same information as 3 equals 12 divided by 4. It's the same thing written in a different way. Okay? So we know anything that we can write with an addition, we can also write with a subtraction. Any relationship we can write with a multiplication, we can also write with a division. Similarly, any relation we can write using exponents, we can also write using logarithms. Okay, so log base 2 of 32 equals 5 is just a different way of writing 2 to the power of 5 equals 32. Okay, log base 3 of 9 is equal to 2. 3 to the power of what gives me 9? Okay, 3 to the power of 2 gives me 9. So this is this information, 3 squared equals 9, written in a log. Log base 3 of 81. 3 to the power of what is 81? 4. So it's using the fact that we know that 3 to the power of 4 is 81 to write it using a logarithm. Log base 4 of 64 equals 3. That's true because 3 to the power of 4, because 4 to the power of 3 is equal to 64. Okay. Log base 5 of 25 is equal to 2 because 5 squared is equal to 25. Okay. Alright, so let's think about that. So again, this relies on, you need to know your powers. You need to know that 2 to the power of 5 is 32, or you're going to find this, quite challenging. Okay, so if we want to complete the following, so let's work down the columns. So we're looking at the same unknown. So log base 2 of 16 is equal to what? So we're asking ourselves 2 to the power of what? If we're counting in a times 2 kind of way, how do we get to 16? So 2 to the power of 4 is 16, which means that log base 2 of 16 is equal to 4. Log base 6 of 36, okay, so 6 to the power of what gives me 36? 6 squared, 6 to the power of 2 gives me 36. And log base 10 of 1 on 1000 equals what? So 10 to the power of what? So this is asking me 10 to the power of what is 1 on 1000. Okay, so remember 1 on 1000 is the same as 1 on 10 cubed, so it's the same as 10 to the negative 3. So this would be negative 3. Okay, let's have a think about the second column. So this time it's the thing inside the log that is missing. So we've got log base 5 of something is equal to 3. So again, it's if we're counting in a times 2 kind of times 5 kind of way, and we take 3 steps, what do we get to? Well, 5 to the power of 3 is going to equal whatever is in here. So this will be 125. Okay? If we're counting in the second one, log base 2 of something equals negative 1. If we're counting in a times 2 kind of way, how many steps does it take to get to negative 1? Okay, so we're thinking 2 to the power of negative 1 equals something. So it's going to be 1/2. So again, this is using the fact that 2 to the power of negative 1 is 1/2. This uses the fact that 5 to the power of 3 is 125. This one uses the fact that 10 to the power of negative 3 is 1 on 1000. Okay, this uses the fact that 6 to the power of 2 is 36. This uses the fact that 2 to the power of 4 is 16. Okay, so the next one, log base 16 of something is equal to 3 on 2. So 16 to the power of 3 on 2 is equal to, okay, and this is where you need to know about your fractional powers, which we did in the last video. So that's, we can think of that as 16 to the power of a half cubed, so that is 4 cubed, and so that is going to be 64. Okay, the third column, it is the base of the log, we call that the base, that is missing. So what to the power of 2 is 81, is essentially what we need to think about in the first statement. So it's 9 to the power of 2 is 81, and so therefore log base 9 of 81 is equal to 2. Okay, so if we're counting in, what steps are we counting in if we need 2 steps to get to 81? What multiplication steps are we counting in? Okay, so the second one in that column, log base something of 7 equals 1. So it is what to the power of 1 equals 7. Well, that would be 7 to the power of 1 that equals 7. So log base 7 of 7 is 1. Log base something of 8 is equal to 1/2. So what to the power of a half equals 8. Okay, so again, you're thinking about what to the power of a half equals 8. Okay, so square root, remember power of half. So square root of what is 8? So it must be 64. Okay, in the next example, we want to take each of the exponential statements and rewrite the same information using a logarithm. So if we know that 5 to the power of 4 is 625, the equivalent log statement is log base 5. So it's really important that the base of the exponent becomes the base of the log. That's always going to be the same. Log base 5 of 625 is equal to 4, because 5 to the power of 4 is 625. If I'm counting in a times 5 kind of way, I need 4 steps to get to 625. Okay, so again, the base of the exponent becomes the base of the log. So 7 to the negative 2 equals 1 on 49, which means that log base 7 of 1 on 49 is equal to negative 2. 27 to the power of a third equals 3. So the equivalent log statement is log base 27, base of the exponent becomes base of the log, of 3 is equal to 1/3. And here, 6 to the power of x equals 20. Okay, so the base of the exponent becomes the base of the log. Log base 6 of 20 is equal to x. And there we've taken an exponential equation that we couldn't solve using our previous methods, which was to try and write both sides of the equation with the same base. And we now have solved for x by converting it to a logarithm equation. Okay, so generally speaking, again, if a is a positive real number other than 1, so remember that's important for our function to be an exponential function. If a to the power of x is equal to y, then the equivalent log statement says that log base a of y is equal to x. This is the first thing we need to get really good at when working with logarithms, how to make that flip between writing something as an exponential, writing something as a log, and how we jump back and forth from that. The key thing is the base of the exponential becomes the base of the log, and the other two things essentially switch sides. Okay. Alright, so then we also want to, we want to start to work on our logarithm laws. So in the same way that that we have index laws, every index law has a corresponding log law. Okay, I'm not going to go into the proofs of those. There are proofs in your textbook. We're just going to look at patterns in numbers and try to make an observation about what we think the log law is. You might remember these from last year, and that's fine, but I want you to follow through the process so that you can see that, you know, why that law is kind of working. Although it's not a proof, but numerically we can see, oh yeah, there is a pattern here, and I can see how I would follow that more generally. Okay, so let's think about log base 2 of 8 plus log base 2 of 4. Okay, so log base 2 of 8 is 2 to the power of what equals 8. Okay, so that's equal to 3. Log base 2 of 4 is 2 to the power of what equals 2, so that's equal to 2. So this thing equals 5. Okay, so what I want to think about is, okay, how could I write log base 2 of just one thing that's equal to 5? Okay, and we know that that would be 2 to the power of 5, so that would be 32 in there. Okay, let's think about the next one, and then we'll do the 4 and then we'll generalize. Log base 3 of 9 plus log base 3 of 81. Okay, log base 3 of 9 is equal to 2 because 3 squared is 9. Log base 3 of 81 is equal to 4 because 3 to the power of 4 is 81. And so this equals 6. So if this thing is equal to 6, okay, let's see if we can write, instead of writing instead of writing two separate logs equaling 6, let's see if we can write one log with a base of 3 equal to 6. Okay, so 3 to the power of 6, I don't actually know that one off the top of my head. Let me quickly grab, my CAS is closed. Hold on, let me pause. Okay, so 3 to the power of 6 is 729, so that means that log base 3 of 729 is equal to 6. Okay, log base 3 of 1/9 plus log base 3 of 81. So log base 3 of 1/9, so 1/9 is 3 to the negative 2, so that equals negative 2. And log base 3 of 81, we had that in the previous question, that's equal to 4, and so here we get 2. So again, let's think about writing that as one log equal to 2. So log base 3 of what is equal to 2? Well, that's 9. Alright, last one here, log base 5 of 5. 5 to the power of what gives me 5, so that's 1. Plus log base 5 of 1, so 5 to the power of what gives me 1, well that's 0, and so this just equals 1. Alright, so log base 5 of what is equal to 1? Log base 5 of 5 is equal to 1. Okay, so what we're seeing here is that log base 2 of 8 plus log base 2 of 4 is the same as log base 2 of 32. Log base 3 of 9 plus log base 3 of 81 is the same as log base 3 of 729. Log base 3 of 1/9 plus log base 3 of 81 is the same as log base 3 of 9. Log base 3 of 5 plus log base 3 of 1, log base 5 of 5 plus log base 5 of 1 is the same as log base 5 of 5. So what we're trying to look at here is how are we combining these two logs into this one log? And it hopefully is pretty clear here that 8 times 4 gives me 32. In this instance, 9 times 81 is 729. In this instance, 1/9 times 81 is 9. In this instance, 5 times 1 is 5. So what we're seeing here is that when we have log base a of m plus log base a of n, so same base, okay, we can combine them together in one log by multiplying. And it's the opposite of the index law that says if we have a to the power of m times a to the power of n, we add the powers. So when we're multiplying powers, we combine them together using addition. When we are adding logs, we combine them together using multiplication. Okay? Let's use this new rule to solve some problems that we couldn't do before. Okay, so log base 6 of 12 plus log base 6 of 3. So the reason we couldn't do this before is because 6 to the power of what equals 12? Well, 12 is not a power of 6, so it's not going to be a whole number. Similarly, 6 to the power of what equals 3? Well, 3 is not a power of 6, so it's not going to be a whole number. However, if we combine these together using our new log law, this is the same as log base 6 of 12 times 3. So that is log base 6 of 36. And then we know log base 6 of 36 is equal to 2 because 6 squared is 36. Okay, similarly in the next one, we can't evaluate those two logs separately, but let's use our log law to combine them together. So adding two logs means we can multiply the things in the logs. So log base 10 of 250 times 40 is log base 10 of 25 times 4 is 100, and then we need 2 extra zeros. So it's 10,000. And so 10 to the power of what gives me 10,000? 10 to the power of 4 gives me 10,000. So this is actually equal to 4. Log base 8 of 3 on 64 plus log base 8 of 1 on 3. Okay, again, can't work out those separate logs, but we can use our log laws to combine them together. So log base 8 of 3 on 64 multiplied by 1/3. Okay, so simplifying those fractions, don't do 3 times 64. The 3's cancel out, and this is 1 on 64. Okay, and 1 on 64 is 8 to the power of negative 2, 1 on 8 squared, and so therefore this is equal to negative 2. Okay, so when we're adding two logs, we can combine them together to a single log using multiplication. Okay, let's have a look at subtraction of logarithms. So again, let's work through the pattern, establish a rule, and then we'll put that into use. So log base 5 of 625 is 5 to the power of what is 625? Well, that's 4. Minus log base 5 of 5. 5 to the power of what is 5? Well, that's 1. So this is going to equal 3. So then the question is, all right, how do I write a single log with a base of 5 equal to 3? Okay, so 5 to the power of 3 is 125. So log base 5 of 125 is 3. Let's do the next one. Log base 6 of 36 is equal to, minus log base 6 of 6. So log base 6 of 36 is 2. Log base 6 of 6 is 1. And so we just get 1. How can we write a single log with a base of 6 equal to 1? Log base 6 of 6. Log base 3 of 9, that's 2. Minus log base 3 of 1. Remember, 3 to the power of what gives me 1? 3 to the power of 0 gives me 1. So that's just going to be 2. And so how do we write a single log with a base of 2? So a base of 3 equal to 2. So 3 to the power of 2 is 9. And then the last one here, log base 2 of 16. 2 to the power of what is 16? That's 4. Minus log base 2 of 32. Well, that's 5. So that's negative 1. How do we write a single log with a base 2 equal to negative 1? Equal to negative 1. and that would be 2 to the power of negative 1, so that would be 1/2. So again, we're looking at here, based on this, log base 5 of 625 minus log base 5 of 5 is equal to log base 5 of 125. This is equal to this. They equal the same thing. This is equal to this, and this is equal to this. Okay, so the question is, how do we get from those 2 logs to that 1 log? What process is happening? And hopefully we've already sort of, well, just logically based on what we saw in the previous set of examples, we can see in this case 625 divided by 5 is 125. 36 divided by 6 is 6. 9 divided by 1 is 9. 16 divided by 32 is 1/2. Okay? And so when we are subtracting 2 logs, we can combine them together as a single log by dividing the things inside the logs. Okay, and again, this is the reverse of the index law that says that if we are dividing 2 exponents, dividing 2 powers, we combine those together by subtracting the exponents. When we are subtracting 2 logs, we combine those together by dividing the things inside the logs. Okay, so it's the sort of reverse thing with the log laws. So let's use this rule to solve some problems. So log base 6 of 72 minus log base 6 of 2. Okay, we can't work either of those out separately, but we can combine them together because we have the same base. So this is log base 6 of 72 divided by 2. So this is log base 6 of 36, and we know that log base 6 of 36 is 2, because 6 to the power of 2 is 36. Okay, log base 10 of 12 divided by log base 10 of 0.12. Again, can't work either of those out separately, but let's focus on combining them together. So log base 10 of 12 divided by 0.12. Okay, so if you have trouble with this decimals and fraction, so think about, I would need to multiply the denominator by 100 so I don't have a decimal. So if I multiply numerator and denominator by 100, I get this. And so 1200 divided by 12 is 100. And log base 10 of 100 is equal to 2. Again, log base 12 of 2 minus log base 12 of 288. Okay, can't work those out separately, but log base, we can combine them together as log base 12 of 2 divided by 288. That's log base 12, of 1 on 144. And 144 is 12 squared, so 1 on 144 is 12 to the negative 2, so this equals negative 2. Okay, this one's a bit less obvious, so I might just go through these a little bit quickly because the pattern's not quite as straightforward. So if I'm looking at log base 2 of 4 cubed, okay, well 4 cubed is 64, so that is log base 2 of 64. 2 to the power of what equals 64? That's 2 to the power of 6, so that equals 6. So my question is, how could we write something of this form also equal to 6? Okay, so log base 2 of 4, that's equal to 2, so we would need 3 times log base 2 of 4 to equal 6. Okay, log base 3 of root 9, okay, well that's, root 9 is 3, obviously, and log base 3 of 3 is 1. So how do we write this is something times log base 3 of 9, so log base 3 of 9 is equal to 2. What times 2 gives me 1? It would have to be half. Log base 5 of 5 squared, okay, well that's log base 5 of 25, so that's equal to 2. Or more immediately, it's very clear, 5 to the power of what gives me 5 squared? It's clearly 2, okay. So how do we make this also equal to 2? Well, log base 5 of 5 is equal to 1, okay, and so something times 1 equals 2 has to be 2 times 1. Log base 3 of 3 to the power of 95, same logic in the previous thing, I don't need to know what 3 to the power of 95 is, because this whole thing is me asking 3 to the power of what gives me 3 to the power of 95, so it has to equal 95. And again, that's equal to 1, what times 1 gives me 95, has to be 95. Okay, so what we're looking at here is this thing is the same as this thing. That is the same as that. That is the same as that. And that is the same as that. So what we're seeing here is when we have log of a power, we can take this power out the front. It's the same as 3 times log base 2 of 4. This is 9 to the half, and we can take that power of a half out the front. It's the same as half times log base 3 of 9. We can take this power out the front. It's the same as 2 times log base 5 of 5. We can take this power out the front. It's the same as 95 times log base 3 of 3. So if we have log of a power, log base a of m to the power of p, we can bring that power out the front of the log and have p times log base a of m. Okay, so again we can solve some problems that otherwise weren't solvable. So we're going to have log base 10 of, that's 1,000 to the power of a half. The square root is a power of a half. So we can bring that half out the front, and we have half times log base 10 of 1,000. Log base 10 of 1,000 is 3, and so we've got half times 3, which is 3 on 2. Here, we can bring the p down the front, so we have p times log base n of n. Now log base n of n to the power of what equals n? Well, that will just be 1. And so this whole thing just equals p. Okay, so here we want to write 3 different expressions, one for each of the laws established so far, that are each equivalent to log base 10 of 36. Now there's no unique answer here, okay? So you can come up with your own answers here, and in fact, pause the video and come up with your own set of numbers here, thinking about what needs to be true of those numbers, okay? So in the first example, log base 10 of 36 equals log base 10 of something plus log base 10 of something. Okay, so we know if we're adding logs, we combine them together by multiplying the things in the log. So as long as the two numbers in these spaces multiply together to give 36, doesn't matter what they are. They could be 6 and 6, they could be 1 and 36, they could be 2 and 18, they could be 4 and 9, whatever. Okay, as long as they multiply together to give 36, that would be a true statement. Log base 10 of 36 is equal to log base 10 of something minus log base 10 of something. So we know we can subtract two logs that are being we can combine two logs that are being subtracted together using division. So as long as this divided by this gives 36, you can choose whatever numbers you want. You could go with 72 divided by 2, you can go with 360 divided by 10, whatever. 36 and 1. As long as the first number divided by the second number gives you 36, it will be true. Log base 10 of 36 equals a number times log base 10 of something. Okay, this one, again, it's a bit difficult to sort of get to the meaning, but if I'm thinking about here is that log base 10, well, 36 is 6 squared, and my last log law told me that I could bring the 2 down the front, so it's the same as 2 times log base 10 of 6. Okay. The last bit is logs of fractions, and this is not really a different log law, it's combining together log laws that we already know, okay? So if we think about, well, log base 3 of 9, that's equal to positive 2, and log base 3 of 1/9 is equal to negative 2. Let's have a look at the second one. Log base 2 of 16, well, that's 4. Log base 2 of 1/16, well, that's negative 4, because 2 to the power of negative 4 is 1/16. So what we're seeing here is actually log base 3 of 1/9 is just negative 1, just the negative of log base 3 of 9. Log base 2 of 1/16 is just the negative 1 times log base 2 of 16. So if we have log of a fraction, we can basically think about the fact that m is m to the power of negative 1, and then we can bring that negative 1 out the front. So it's negative 1. So what we're really thinking here is, well, this is the same as log a of m to the negative 1. My log laws tell me the negative can come out the front. So it's the same as negative log a of m. Okay. Same idea with taking a reciprocal. So here, this is the same as log base a of m over n to the negative 1. And so you can take that negative 1 down the front, and this is the same as negative 1 times log a of m over n. And then a couple of additional facts about logarithms. If we take some exponential facts we're familiar with, the fact that a to the power of 1 is equal to a, and rewrite that using a logarithm. So remember, base of the exponent becomes the base of the log. The other two things sort of switch around. The equivalent log statement is log base a of a is equal to 1. We also know that a to the 0 equals 1, and so the equivalent log statement for that is that log base a of 1 is equal to 0. Right, so there's a summary of your log laws. Really, you've essentially got 3 main log laws. these three here. The others are all really extensions of those. These are simply converting your, you're just simply using your understanding of logarithms. A to the power of what equals a? It's 1. When we write a log without a base, so if you just write log x, the implied base is 10. Okay, so the default base for a logarithm is 10. It's called the common logarithm. So if you leave the base out, we're assuming that you mean base 10. If you don't mean base 10, you must make sure that you write a base. Okay, there's another, not another common logarithm, but another logarithm we use frequently called the natural logarithm, which has a special base that's a number called e, and we'll talk about that a bit further on in the topic. When you're using your CAS to work with logs, there is a log button. Well, you press Control 10 to the power of x, it's above there, and then you simply enter the base in the box for the base and the other number in the brackets. If you leave the box for the base blank, it will assume base 10. So yeah, that's where you're going to go to enter your logarithms. Okay, so today there's a combination of work from exercise 13E in your textbook and then additionally a worksheet to be working on as well.